analysis that we want to have by conducting these analysis. So before I start, how many of you actually went through the notes shared by Neil? Have you all gone through the notes at least once till the point what we have covered so far?
Yes, sir.
Yes, sir.
Okay, okay. What others? Is there anyone who has not gone through? Please be honest. Is there anyone who has not gone through the notes yet? I'll not say anything, just be honest.
Sir, I have gone through, but I understand very little, sir.
Okay, fair enough. What about others? Okay, so except for Mihir, I'll assume that all of you have gone through the notes, right?
Yes, sir.
Okay, okay. Okay, so far we have discussed the assumptions of classical linear regression model, and out of the several methods used to estimate those unknown population parameters as far as linear regression model is concerned, we discussed one of the most used and taught methods in econometrics, which we call as ordinary least squares. In short form, we call it as OLS method. So वहाँ पे हमने क्या देखा? All these assumptions of CLRM, we assume all of those assumptions about the population. You know कि जो population में जो variables हैं, whether they are explanatory variables or explained variables or dependent variables, they are jointly distributed. And why I'm saying jointly distributed, if you remember from our earlier lectures, I told you that these are conditional distribution. So we assume them to be jointly distributed, and that too in a linear relationship. And by linear relationship, what we mean is that the dependent variable is expressed as linear combination of the regressors that we as a researcher think to be having certain impact on the variation in Y, plus a stochastic term about which we assume that the probability distribution of this stochastic error term follows a certain well-behaved distribution, where we say that the conditional average or expected value of the error term conditioned on the data is 0, and then the assumption of homoscedasticity gives the variance of the error term and the error term of the population. अब अगर मेरे पास सारा population होता तो sampling की बात ही नहीं है. If I know the entire population, I can, if I want to talk about the average income level of residents of Pune, and if I have the entire population with me, I do not need to talk about sample at all, because I have the data for all the individuals or all the individual residents of Pune. So precisely, we do not have the data on the entire population. We proceed with this idea of what is called as sampling. बहुत different तरीके के sampling होते हैं, and I had requested you to go through certain textbooks, and recently CMI has also released their sampling methods. So हम sampling पे जाते हैं. So we collect observations on these variables, which we call as explanatory variables and dependent variable. We collect observations on them, And then we assume that this sample that we have collected is a representative of the population about which I am trying to estimate, I am trying to guess. And that's where you have sample regression function. So sample regression function is a estimate of the population regression function. And the moment we talk about sample regression function, it means the estimators of the population gets estimated by the sampling parameters. And then to estimate this population parameter, one of the most used method, that's what we have discussed as of now, is ordinary least square method. Why it is called least squares is that this method presupposes, or this method, the principle of this method is to find out such values of sample parameters which leads to minimization of residual sum of squares. So the sample counterpart of errors in the population is residuals in your sample, and we want to select such values of OLS estimators which gives us the minimum value of residual sum of squares. This principle funda tha OLS ka. And after that, whatever we have done is just a mathematical manipulation of, or you can say algebraic manipulation of the principles that are followed in the method of OLS. So we wrote the residual vector in the form of y and x. Then we calculated the residual sum of squares. And the very principles of minimizing something, we followed that process. We calculated the residual sum of squares. It's a function of the variable b, that is your sample estimators or OLS estimators. So we differentiated the residual sum of squares with respect to these estimators, equated it to 0. What we got was called normal equations. And that's where you have, b is equal to x transpose x ka inverse multiplied by x transpose y. That is a normal equation that we generate. And why it is called normal? Because in the geometry of least square that we had discussed in our previous lecture, we say that when we write y is equal to xb plus residual, that xb component is nothing but the linear combination of all the regresses that are used in the model, plus a random component which tells us that y does not lie in the linear combination space of the regressors. Instead, it lies outside that plane, and hence, in order to best estimate about the actual y values, we select such values of b which takes us exactly below to the point where actual y values are there in the space outside this linear combination. And then we drop a perpendicular from this actual y values to the estimated y value condition on the data. This becomes your error term. And that's why the equation that we generate by the method of, or by the principle of least square, those equations are called as normal equations. And that's why we were able to write y, that is actual y value, as a sum of two orthogonal components, whereas the first component is your non-stochastic component, which are nothing but the linear combination of the regressors. And the second component is your error term, which is the stochastic component of the y value. And then we had talked about the decomposition of sum of squares, TSS, ESS, RSS. Then we talked about R square. What is R square? R square just tells us the proportion. Ultimately, you have to understand that we are concerned about the variation in y values around its mean value. Because the way we had interpreted the regression equation in our previous lecture is that whenever there is slight increase or decrease, or we can say slight change in the value of the regressor on an average, how y changes. So the sample regression line है आपका, all the points on that sample regression line is nothing but the conditional mean value of y on the sample observations. So the individual y में, for a given x, let's say, for a given x, we have 5 observations on y. So 5 observations on y है, तो इसका easily मैं mean value निकाल सकता हूँ. And what I'm concerned about is that how these individual values of y are centered or are distributed around its mean value. So y में जितना भी variation है, उसकी कितने proportion of variation को मेरा explanatory variables explain करता है, that is what R square is. So the proportion of total variation in y explained by the linear combination of regressors in the model is nothing but your R square. And the rest, which is not explained by the regressors, we call them as residual sum of squares. That is, it is that part of variation in y which does not get explained by the linear combination of the regressors. So आपका R square you easily calculate as ESS upon TSS, and then we had discussed that R square is a function, or we can say is a non-decreasing function of the number of explanatory variables in the model. अब इसका लॉजिक क्या है इसके पीछे कहने का, देखिए, whenever you include an additional explanatory variable in the model, what it means is, or what would have guided the researcher to include this additional variable explicitly in the model is that there's some impact this additional variable has on the variation in y, and that's why there'll be slight increase or some increase in the explained sum of squares. And that's why if you keep on adding additional number of variables in the model, your ESS may or may not increase, but it will never decrease. And that's what precisely explains that R square is a non-decreasing function of the number of explanatory variables in the model. And then we discussed that since we are trying to estimate about the population using sample, it means we have certain limited number of observations at our hand. और अब जो भी observation है मेरे पास, just give me a second guys. Hello? हाँ उल्लास भाई लेक्चर में हूँ. हाँ बोलो. हाँ बोलो. वही मैं चेक करने के लिए बोला था, एक बार आते हुए उसे चेक करो कि सेक्शन बी में उसका नहीं था पेपर. नहीं, देवम पांडे का मैं देखा था बट आई कुड नॉट फाइंड. तो एक बार आप आते हुए उनसे चेक कर लीजिए और अगर उनके पास होगा तो फिर मुझे दे दीजिएगा. जी जी हाँ हाँ. किसको? याद नहीं मुझे उल्लास भाई. अच्छा ठीक है, एक बार चेक कर लूंगा मैं. हाँ 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 ओके. हाँ हाँ जी 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 चलेगा. ओके. Yeah. So since we are using sample to estimate about the population, we have limited number of observations at our hand, and that's why if we keep on adding the explanatory variables in the model, that many parameters first I have to estimate, and that estimation is based on the sample observation at my hand. And that's why there's this concept which is called as degree of freedom, which comes into picture. And precisely this R square consumes those many number of degrees of freedom as you keep on including the additional explanatory variables. तो लोगों ने इसका एक They just tried to find a way around this, and that's why a new statistic they could come up with, and that was called as adjusted R square. So adjusted R square takes care of these degrees of freedom into account. And what it means is that if you keep on adding additional number of redundant explanatory variables in the model, it keeps on imposing a penalty. And if you just add several numbers of explanatory variables which do not explain additional variation in Y, your adjusted R square might turn negative as well. And that's why adjusted R square is a better statistic as far as we have to compare two models on the same question, on the same research question, which differ in their form of specification, especially in the number of independent variables used in the model. तो ये रहा अभी तक का समरी जो हमने डिस्कस किया, जो हमने पढ़ा है अभी तक. And in the last lecture I had also introduced this idea of expressing equation in deviation form, and that's what we'll discuss in brief, and we move forward and discuss about the statistical inference using these OLS estimators. Am I clear till here?
Yes, sir.
Okay. Can you all see the screen now?
Yes, sir.
Okay, all right. So you need not write any of the things that I mentioned, at least till the point where we are discussing OLS and assumptions of OLS and equations, because all those things are already covered in the notes. Just understand these portions and then we are good to go. Okay, equation in deviation form क्या बोलता है कि जो आपके पास raw observation है, जो मेरा equation है, if I write y is equal to xb plus e, what it says that you can express this entire sample regression function exactly in the deviation form. Deviation of what? Deviation of these raw observations around its mean value. So we simply write y our sample regression function as this, assuming that there are k number of explanatory variables. Then we average this whole equation over the sample values. So that is, if I have n number of observations, that's what I written. I goes from 1 to n. So if I average this y1 plus y2 plus y3 so on till yn divided by n, it gives me y bar. Similarly, this is a constant term, so its mean value will be b naught here. N times beta naught divided by n, so you'll get b naught. This is the coefficient b1. अब ये xi1 है. It means what? x11 plus x21 plus x31 से लेके xn1 divided by n, and that is nothing but your x1 bar. So इसी तरह मैंने सारे जितने भी sample observation है उसका मैंने average out किया. So I get this equation. I call it as 1, I call it as 2. If you subtract equation 2 from 1, what you get is yi minus y bar. Yi minus y bar is your expression of dependent variable around its mean value. So this is the deviation form. And जो normal terminology है या common terminology है, जितने भी आप books में देखोगे, all the variables which are written in the deviation form, and the moment you read this term deviation form, you have to understand that what I'm talking about is that expressing these raw observations taking as difference around its mean value. That's why they're called as expression in deviation form or equation in deviation form. So yi minus y bar, b naught cancel हो जाएगा, b1 bracket में xi1 minus x1 bar, और इस तरह करके you go till here. Here I've written e bar is equal to 0. That's what we have, it comes from your OLS. And finally, this is my equation in deviation form, where I have written deviation form. Generally, they are denoted by small letters. So yi, small yi, you must understand this small yi is nothing but yi minus y bar. Why exactly, we are talking about expressing these sample regression function or sample regression line exactly in deviation form is because it reduces the amount of calculation. Otherwise, you would have had to calculate had you gone with the method of, or gone with the process of the raw observations, and that's what the exact purpose of expressing these in deviation form. So this is my sample regression function expressed in observations of deviation form, where yi is yi minus y bar, xi1 is xi1 minus x1 bar, and so on, so forth. Now, precisely what we have obtained above, it can be obtained using a very important matrix. And let me tell you beforehand only, whatever matrices or whatever matrix that we'll discuss, or that econometrics, as far as econometrics is concerned, we mostly use the properties of square matrix, and especially we utilize the properties of those square matrix which are idempotent and symmetric. So जितना भी आप matrix देखोगे, जितना भी matrix use होगा, mostly वो symmetric होंगे, idempotent होंगे. Idempotent matrix का मतलब ये हो कि अगर आप matrix को खुद से multiply करोगे तो वो उसका value change नहीं होता. That's what it means. So we use a transformation matrix which is defined as A. We call it as A. That's what I have used. Name it anything. A is IN. This is your identity matrix of the order N. I'm sure that you understand what identity matrix is. Identity matrix are those matrices where the diagonal elements consist of 1 and all the non-diagonal elements are 0. And it has a dimension of n, means there are n number of rows and n number of columns. So in minus 1 upon n, I transpose. Ab I kya hai? I is a column vector consisting of n number of ones. तो ये क्या बोलते हैं, इसको ट्रांसफॉर्मेशन मैट्रिक्स क्यों बोलते हैं? इसका ये है कि if you pre-multiply this matrix by a vector of variable, it will transform that vector of variable into deviation form. एक बहुत ही सिंपल एग्जांपल लेते हैं, छोटा एग्जांपल लेते हैं. सपोज मेरे पास है y1 y2, ठीक है. This is a vector consisting of 2 number of elements, and I want to express this column vector consisting of raw observations around its deviation or around its mean value. That is, I want to express this in deviation form. So ultimately I want to talk about y1 minus y bar, y2 minus y bar. This is what I'm interested in. अब ये देखिए ट्रांसफॉर्मेशन मैट्रिक्स का कैसे यूज करते हैं. सिंपल एग्जांपल है. तब ये क्या है? Identity matrix of the dimension n, 1 upon n, I transpose. Here, since I have n is equal to 2, I'll take A as I2, 1 upon 2, I transpose. So I kya hai aapka? It will be a column vector consisting of 2 number of ones. It gets post multiplied by its transpose. So 1, 1. Now if you see, it will become a matrix. This is a dimension 2 by 1. This is a 1 by 2. So this will become 2 by 2. That is n by n. So 1, 1, 1, 1. ये मेरा आ गया I transpose, and this entire thing is divided by 1 by 2. Right? Now ये क्या है मेरा? ये I2. That is identity matrix of the order 2. Now this transformation matrix will get post or pre-multiplied by this vector of y. So I can write this here. So this will become what? Y1 times 1 by 2 plus y2 times 1 by 2 is nothing but your y bar. Y1 by 2 plus y2 by 2. Y1 plus y2 by 2 is nothing but your y bar. Similarly, y1 times 1 by 2 plus y2 times 1 by 2, this will also be y bar. So y1 times, y times this, I have got y bar. अब ये मेरा इससे भी multiply होगा. अब ये I2 क्या है? I2 is 1, 0, 0, 1, identity matrix, right? Minus of, I have already got y bar, and this will get multiplied by y1, y2, because ultimately, So now you see what happens over here is y1 times 1 minus y2 plus y2 times 0. This will become y1 minus of y bar. Y2 times, y1 times 0 plus y2 times 1 is equal to y2 minus y bar. This will give me y2 minus y bar. So ultimately what I get is small y1, small y2. And that's why precisely this transformation matrix, or written in this form, they are called as transformation matrix. Meaning what is that if you pre-multiply such matrix with a column vector consisting of certain variables, not just column vectors, if you pre-multiply this matrix with any vector or combination of vectors expressed in matrix notation, it transforms all such raw observations into deviation values. Am I clear till here, all of you?
Yes, sir.
Yes,
Yes,
sir. I had a small doubt, sir.
Haji.
Sir, we are calculating the variance from the mean, no, in this transformation matrix.
Come
If
again,
I'm
dear?
not mistaken, we are calculating the variance, no, sir, from the
We are
distance
not-
from the mean.
Yeah, distance from the mean, correct.
Yeah. Thank you, sir.
Okay. Okay, so let us move ahead and see how this transformation matrix can be easily utilized as far as expressing sample regression in deviation form is concerned. So this is my sample regression function. Y is equal to xb plus e, where x is your data matrix, b is your coefficient vector, and your e is your residuals. So what I've done here is I've expressed this data matrix or I partitioned this data matrix exactly into two portions, where I have, so you can think like this. So x मेरा क्या है, जो मेरा data matrix है, वो क्या है? उसका जो पहला column है, it is reserved for those intercept term, and those के बाद जितने भी columns है, those are mainly for the number of explanatory variables used in the model. So that's what I've done. I have divided, or I have partitioned this entire data matrix exactly into two parts, where I have just written the column consisting, or column vector consisting of n number of ones, or whatever number of elements, or whatever number of observations that we have. I've separated this column consisting of 1 from the rest of explanatory variables in the model, right? So you understand this. So this I is a column vector consisting of number of ones, and x2 will be what? x2 is number of explanatory variables in the model. So its dimension क्या होगा? Still you have n number of observations, but now the dimension of this x2 will be k minus 1, because you have already excluded the intercept term from this data matrix, and it will it will be n by 1. So partitioning का यही purpose, और partitioning का एक ही main important condition होता है that you can partition a matrix in any form provided the sum of the dimensions of all the partitioned matrix must be equal to the dimension of the whole matrix. That is you have to always keep in check. And then I have also partitioned this coefficient vector consisting of those OLS estimators exactly into two portions. So this is my B naught, which is just reserved for this intercept term. And then now this B1 is a vector. B1 is a vector means what? Now this B1 vector consists of all those K minus 1 OLS coefficient estimators or coefficient parameters. So I just written residuals as it is. Now if I pre-multiply both the sides of this expression by A, that is your transformation matrix, you can write A times Y, A times this plus A times E. Now you see what happens over here is, now A times Y means what? This Y consists of, or is a column vector consisting of n number of observations on the raw values of Y. I pre-multiply this Y with the transformation matrix. So what I'll get is Y1 minus Y bar, Y2 minus Y bar, so on, Yn minus Y bar. And in short, I have written them as small y star. So A times Y is your small y star. Now A times multiplied by this, so A times I kya hoga? I is your column vector consisting of ones. अब A times I means what? ये ट्रांसफॉर्मेशन मैट्रिक्स, इसका मतलब क्या हुआ कि अगर मैं इसको प्री मल्टीप्लाई किया A से, so it will transform this column vector consisting of ones into its deviation form. अब if this is a column vector consisting of 1, the mean of this whole observations will be 1. So 1 minus 1 will be 0, 1 minus 1 0, 1 minus 1 0. इस तरह nth term will also be 0. So what it means is that A times I will be 0, and that's why this term goes. Now A times x2 will be what? You have this data matrix, that is column expressing the observations on those explanatory variables gets pre-multiplied by the transformation matrix. What it means is that now each of the column which consists of the observations on the explanatory variables, all of them get expressed in the deviation form. That's why I've written here is x star times b1, and A times E will be E. I ask you to verify it yourself, because mean of E is 0. So expressing the residuals in its deviation form is nothing but the residual vector itself. So A times E is equal to E, and that's why I've written like E over here. So now this becomes my y star is equal to x star b1. You could have simply written y is equal to x b1 plus E. There is no issue. So now this is your equation in deviation form, and what you notice over here is that when you express this OLS equation in deviation form, there is no intercept term. It means when you express the equations in deviation form, you simply take the level of series to be 0. That is, now you assume that your sample regression line passes through the origin. That's what it means. Okay, all right. So, and I know that x transpose E is equal to 0, because there's zero covariance between the residuals and the sample observations. It also automatically means that x star transpose E will also be 0, because the x star transpose is nothing but the deviation observations. And if I pre-multiply both the sides of expression by x star transpose, so it will become x star transpose times y star is equal to x star transpose times x star times beta 1 plus x star transpose E. This will become 0. So what you notice over here is that I get B1 as x star transpose x star ka inverse multiplied by x star transpose y star, and this is nothing but your normal equations expressed in deviation form. And that's why in the last lecture, when we had solved the question also using the deviation form, if you expand the normal equation which you usually write for the raw observations, and when you express them in deviation form, the first row and the first column will go out to 0, and that's what this division form is all about. Now if you express this equation in division form as sum of squares, so this will automatically become your TSS is equal to ESS and RSS, and that's how you calculate R square as ESS upon TSS. I need not explain this in great detail now. Let us look at this quantity, which is nothing but your adjusted R squares. So adjusted R square kya hai? Adjusted R square is defined by this formula: 1 minus RSS upon n minus k. K is your number of explanatory variables, n is your number of observations. So RSS जो है residual sum of squares, उसका degree of freedom होगा n minus k. Can you guess why? Anyone?
Could you just repeat your question, please?
Why the degree of freedom of residual sum of square is n minus k?
Sir, in the n number of explanatory variable, there is the k number of explanatory variable used in that model.
Okay.
So the kind of penalty that maybe.
But why not TSS has the degree of freedom n minus k?
Sir, I think TSS can directly be found just by knowing all the values of your Y. So So when you know all the values of your y, you do not need to know about x1, x2 values. So given that fact, you only have one thing which is restraining you, and hence n things which are giving you information. So n minus 1 is excuse me, the degrees of freedom for TSS. Meanwhile, to find RSS, you have to first define your model, and once you get your model, then you find your RSS. Now n things give you information and k things restrict you. So the degrees of freedom will be n minus k.
Correct. Very good. Okay, you see why the degree of freedom for RSS is n minus k, as Neil correctly pointed out. You see, TSS क्या है आपका? The answer lies in the formula itself. TSS is summation yi minus y bar का whole square. So in order to calculate this TSS, the only thing which I need to know is this mean value, right? So if I have n number of observations, in order to calculate TSS, I need only one restriction on all these raw observations. That is, I have to calculate mean values, and that's how I'll get easily TSS. So if I have n number of observations, out of this n number of observations, one value is fixed. That is a mean of y. So that's why TSS, that is total sum of squares, which is nothing but the variation in y, has n minus 1 degree of freedom. Whereas residual sum of squares क्या है? Residual sum of squares निकालने के लिए मुझे E transpose E की जरूरत है, और E निकालने के लिए I need to have this model y minus x beta xb. अब अगर मेरे मॉडल में k number of explanatory variables used हैं, it means out of the n observations that I have, first I have k number of parameters to estimate. It means out of n observations, I'm only free to use n minus k number of observations if I have to calculate residual sum of squares. And that's why RSS has a degree of freedom as n minus k. And if you simply do the math, you can easily find that ESS will have degree of freedom as k minus 1. Because ultimately TSS must be equal to ESS plus RSS. इसका डिग्री ऑफ फ्रीडम है n माइनस के, इसका डिग्री ऑफ फ्रीडम है n माइनस 1. सो जो बचा इसका डिग्री ऑफ फ्रीडम होना चाहिए k minus 1. So that's why your ESS will have a degree of freedom k minus 1. And when we discuss the analysis of variance test where we use this ESS, what you'll notice is that in the numerator portion, the degree of freedom, or the numerator gets divided by degree of freedom, which is k minus 1. And then, the relation between adjusted R square and the unadjusted R square is given by this formula. And, I'm not going to explain this in great detail. And if you just do a little bit of algebraic manipulation, you can easily find out the relationship between adjusted R square and unadjusted R square is given by this formula, where k is your number of explanatory variables, n is your number of observations. I request you to find out under what conditions adjusted R square will turn out to be negative. Just see this formula and find out the conditions under which adjusted R square can turn out to be negative. So keep this as homework. I request you to find out this portion. Okay, I have written this SIC and AIC, which I'll not discuss now. I'll discuss this, once we are done with the inference procedures. All right. So, abhi tak ye tha ki, how do we exactly express equations in deviation form?
Sir, one question. I didn't understand the question above. Like R square negative कब होगा, but वो तो R square है ना?
मैं adjusted R square की बात कर रहा हूँ, dear.
Okay, so we have to find out when will adjusted R square be negative.
Correct. So what should be the conditions? And let me tell you the hint, it will be based on n and k. So under what condition adjusted R square turn out to be negative? And if I'm not mistaken, this was asked during my days. I'm not exactly sure, but they asked this question when I was preparing for various entrances. So just try finding out this. Okay, all right. So now moving on, what we have discussed till now is the OLS estimators. हमने normal equation पढ़ा, हमने mathematical calculation देख लिया कि OLS कैसे निकालते हैं, and that's where we had found out that X transpose X inverse X transpose Y is the normal equation that we get. Now, what is the purpose of finding out the OLS estimator? क्या purpose exactly? So the purpose of finding out OLS estimator is because ultimately this OLS estimator, if you actually see it, is based on the sample observation. And why do we calculate it? We calculate it to estimate the unknown population parameters. It means somewhere through these OLS estimators, we want to talk about or we want to draw inferences about the population parameters. So in order to talk about the statistical properties of OLS estimators, we need to assume certain things. Let me repeat what I have talked till now. What I'm saying here is, in order to establish the statistical properties of these least squares estimator, we need to assume certain thing about the way relationship are specified, and those are the assumptions that we have already understood. But as far as the inference procedures are concerned, some additional, not additional you should think, but the main two assumptions that we need in order to proceed ahead with finding out the statistical distribution or probability distribution of these OLS estimators. The first assumption that we have is, we assume since B depends on XS, so we assume that X is non-stochastic and it has full column rank. अब देखिए नॉन स्टोकेस्टिक का मतलब क्या है? What it means is, since B, this your OLS estimators, depends on the sample observations, so your inferences that you want to have on the population parameters, it will also be conditional on the sample values of the X variables. And once you have collected the observations on the X variables, that is assumed to be fixed for that particular sample. Only if you change the sample observations, your B is going to change, and that's why your inference about the population parameter will also change. But as long as you have calculated your OLS estimator based on one particular sample observation consisting of all the observations on the explanatory variables and dependent variable, that is assumed to be non-stochastic, meaning what? That elements of the X matrix, they are treated as fixed in repeated sampling. And it has a full column rank. हमने देखा था assumption number 2, which is also called as identification condition, कि अगर X का full column rank नहीं होगा, since we have written the normal equation in the form of X transpose X inverse, X का जो rank होगा वही rank X transpose X का होगा, and if X does not have full column rank, will not be able to obtain X transpose X का inverse. And if you are not able to obtain X transpose X का inverse, will not be able to uniquely determine the values of the OLS estimators, and that's why it is called as identification condition. So X, as far as inference procedures are concerned, X is assumed to be non-stochastic and it has full column rank. And the second assumption, we are quite familiar with this assumption, is that random disturbances of the population has this following properties, is that expected value of these random disturbances is 0 and variance of u, I'm not writing subscript, but you have to understand that I'm talking about the error, or sorry, the random disturbances term for each of the observation. The variance of u is a constant term written as sigma square. Later on, when I write this in matrix notation, I'll write this as sigma square multiplied by this identity matrix. But just for the time being, I am not writing this. But you have to understand that you have to multiply this with the identity matrix. What it means is, let us try and focus on this portion. अब हमने पिछले कुछ lectures में ये देखा था that if I have to talk about, if I have to obtain sum of squares in matrix notation, what I do is I take the vector and I pre-multiply this vector by its transpose. Now, if you have to obtain the variances of variables, what we do is we take the variable in vector notation and post multiply this vector by its transpose. So if I have to talk about variance of the disturbance system, what I write, how do I write here is expected value of u transpose. That's how you write, variance in when you have a probabilistic, nature of variables. Expectation always comes into picture when you have probability of, occurrence of certain variables. So अगर मान लेता हूं मेरे पास n number of observation है, तो मेरा जो u होगा, that is column vector consisting of n number of observations on the disturbance system, can be thought to be written as like this. Now it gets post multiplied by its transpose. ये column vector था, तो ये row vector बन जाएगा. Now you see this has a dimension n by 1. This has a dimension 1 by n. Multiplication of matrix is conformable, and the multiplied matrix will have a dimension n by n. So it will be a square matrix and it will also be a symmetric matrix. So जब आप इसको expand करोगे u transpose को, what you'll notice here is u1 times u1 multiplied by un times u2, un times u3, so on till un times un. So first जो observation होगा, सब में expectation होगा. So I'm just writing expectation outside, but you have to understand that this will be something like this. Similarly, u2 times u1, u2 times u2, so on till u2 times un, and इसी तरह it will be un times u1, right? अब expectation ही पूरे matrix पे लगा हुआ है. What it means is that each element of the matrix will also have expectation attached to it. So अब first term को देखिए आप. This is expected value of u1 multiplied by u1. That is, you're talking about the variance of u1. Now this is expected u1, u2. This is nothing but your covariance of the first error term with the second error term. By the same analogy, expected value of u1 times un is the covariance of the first error observation with the nth error observation. और हमने जब assumption हम देख रहे थे, तो we had noticed that we assume that not only variances of the error observations are constant for each observation, also the auto covariances of the error term is 0. What it means is that only the elements on this principal diagonal, which are nothing but the variances of the each error observation, they are sigma square, sigma square, sigma square, sigma square, and rest, since all these non-diagonal elements are nothing but the covariances, they are 0, 0, 0. So now this is your variance of error term, and this can easily be written as, if I take sigma square common, this can be written as sum 1, 1, 1, 1 ho jayega, rest all are 0. So this will be your written as sigma square times identity matrix, and this can also be written as expected value of mu mu transpose. So this is what we assume about the distribution of the error term as far as the inference procedures are concerned. That is, we need these two assumptions when we talk about the inference procedures based on the OLS estimators. Now, matrix that we have just obtained, this matrix is called as variance covariance matrix of the disturbance system. Whereas the variances of the disturbance system, they are displayed on the main diagonal element, and the covariances of the disturbance system, they are expressed on the off diagonal positions, or they are not on the diagonal positions. So if you actually remember the assumption of disturbance system, that while we were discussing the classical linear regression model, this combined assumption of homoscedasticity and non-autocorrelation is referred to as the assumption of spherical disturbances. So now proceeding ahead with these two assumptions in our mind, what we intend to do here is,
what is it called? Spherical what?
Spherical disturbances. Assumption of spherical disturbances, which is combination of homoscedastic error term, that is equal variances error term, and non-autocorrelated error terms. The combination of these two assumptions, they are called as spherical disturbances. So what we intend to do now, we intend to calculate, or since B, that is your OLS estimators, it is a function of sample values. So if you keep on changing the sample values, your B changes. So it must mean that B also will have certain distribution function or probability distribution. Now, in order to characterize probability distribution, we need to find out the parameters of that probability distribution. And that's where you have, these concepts which are called as measures of central tendency, measures of dispersion, kurtosis, skewness, and all the higher moments of distribution. They're also called as moments of distribution. And moments of distribution are nothing but the power attached to the observations expressed in deviation form. That's what moments of distribution is all about, and it has been taken from the physics, where you have this ultimately moments of distribution क्या बोलता है आपको, अगर आप actually logically देखो तो क्या है ये mean, variances, skewness, kurtosis. What it tells you is that I have a variable, I have a random variable which occurs with a chance, and each occurrence has got certain probability attached to it. And if it is a probability distribution, one of the first condition that it has to satisfy is that the sum of the probability of occurrence of each of the individual variables has to be equal to 1. That's how you calculate that probability can never exceed 100%. And then we calculate a representative value of all the observations that we have. जैसे क्लास का आपका मॉनिटर या क्लास का रिप्रेजेंटेटिव होता है, या लेट्स से इफ आई वांट टू टॉक अबाउट कि एवरेज हाइट लेट्स से इस क्लास ऑफ एमएससी इको और एमएससी एफई का कितना होगा. So what I do is I take each of the individual observation, in this case humans, I record their height and I calculate an average value of all the observations. That gives me a representative number. कि जो एवरेज वैल्यू है सारे इंडिविजुअल्स का इस क्लास में ये है, लेट्स से 5 feet 4 inches. Now it does not mean, now you must understand that this average value itself is based on the observations in the sample. But it does not mean that all the individual observation will be exactly equal to the mean value. It cannot happen. It can only happen if you have a uniform distribution, which we are not talking right now. So then what we want to find out is कि चलो ठीक है ये तो representative value हो सकता है कुछ बच्चे बहुत ही लंबे हैं, let's say they are if there are 50 students in the class, 10 students are above 655 inch. It automatically pulls up the average height of the class. So we want to have an accurate measure. That's when we talk about measure of dispersion. That is how individual observations are spread or distributed around the mean values. And that is also in other words called as variance. There are other measures of dispersion as well, like range, quartile division and all. But one of the heavily used method is variance. So it is exactly mean and variance of B which we are interested in finding out. So let us, and I'll talk about mean and variance of B, then I'll wind up the lecture. But just give me some minutes. So I know that B जो है मेरा by the normal equation, it is expressed as X transpose X inverse X transpose Y. Now, if I write this Y in the population regression notation, so I can write this as X transpose X inverse X transpose, Y की जगह I can write X beta plus mu. Now you see, if I expand this, this will become X transpose X inverse multiplied by X transpose X beta plus X transpose X inverse X transpose mu. Now this term, X transpose X inverse multiplied by X transpose X, this will become identity. So I can easily write this as beta plus an additional term will be there, which is your X transpose X inverse X transpose mu. Now I want to talk about the mean of B means what? Expected value of B. Right? So if you just take this B on the left hand side, I can write this as B minus beta is equal to X transpose X inverse X transpose mu. And then I have to talk about finding out the mean value. It means I'll apply expectation operator both the sides. Now you see here, the assumption of non-stochastic data matrix or X will come into picture. अब ये expectation है, ये whole term पे applied है. But you notice that since X is assumed to be non-stochastic, even this term will be non-stochastic and this will also be non-stochastic. It means it is not random. And if it is not random, you can easily take these terms out of the expectation parenthesis. That is, in other words, you can simply take this expectation parameter or expectation operator right ahead of the only stochastic term in the expression, that is mu. So I can write this as X transpose X inverse X transpose expected value of mu is equal to expected value of B minus beta. And again, this, by the assumption number 2, this will go to 0. So this right hand side will be equal to 0. And if you take if you just expand this, it will become expected value of beta. Ab ye beta ek to, population parameter. So expected value of beta has to be beta, must be equal to beta. So mean of OLS estimators are always equal to the true population parameter, and statistics में जब भी आप estimator क्या होता है? Estimator is a statistic which you use to talk about the population parameter. It's like sample mean. Sample mean is also an estimator. Sample variance, sample covariance. sample correlation. These all are an example of estimators which we use to estimate about the population mean, the population covariance, the population variance, and so on and so forth. Now, what do I mean by this is, we simply, without even thinking, we write x bar as x1 plus x2 plus xn upon n. This is at best the best guess about the true population mean of x. And when I say it's the best guess, you must always, understand that whenever you talk about guess, there has to be some element of error attached to this guess. But why? We simply write sample mean like this because ultimately we assume that all the individual errors which are there related to each of these observations, they are 0. And that's why sum of E1 plus E2 plus E3 so on till En divided by n goes to 0, and you simply write sample mean as this term. But this is a statistic. This is an estimator. So mean of OLS estimator is the true population parameter, and in statistics, such kind of property of estimator are called as unbiasedness. That is, when expected value of your estimator is equal to the true population parameter, that estimator is said to be an unbiased estimator of the true unknown population parameter. But you always have to understand that this I was able to calculate as long as this holds. That is, average of all the associated disturbances term are 0. अगर ये नहीं होता तो ये हम नहीं ला पाते. You have to understand this. So your OLS estimators, which are based on sample observations, they are an unbiased estimator of the true and unknown population parameter. Now let us go ahead and talk about the variance of B. अभी हमने जस्ट देखा था कि अगर मुझे वेरिएंस एक्सप्लेन करना है या वेरिएंस लिखना है मैट्रिक्स के नोटेशन में, आई कैन सिंपली राइट वेरिएंस एज एक्सपेक्टेड वैल्यू ऑफ, अभी हमने बी, और वेरिएंस क्या होगा, स्केलर नोटेशन में वेरिएंस आपका ये है. मैट्रिक्स में क्या हो जाएगा, मैट्रिक्स में दिस वेक्टर विल गेट पोस्ट मल्टीप्लाइड बाय इट्स ट्रांसपोज. Let me write it. So I can write this as expected value now if you simply expand this is nothing but a variance of B, और B minus beta भी हमने देखा था, B minus beta, sorry. You see, B minus beta is this term, X transpose X inverse multiplied by X transpose mu. So I'll simply write it here, expected value of X transpose X inverse, X transpose mu. Now this gets post multiplied by its transpose. अब A B का transpose is B transpose A transpose. हर एक term को आप वैसे देखो, A B C का transpose will be C transpose B transpose and A transpose. If you keep on transposing it, so mu ka transpose will be mu transpose, X transpose ka transpose will be X, and X transpose X inverse ka transpose will also be X transpose X inverse. So I can write this as in this notation. Now, you see, again, this whole expression has an expectation operator. An expectation operator can be simply moved across from those variables which are non-stochastic in nature. So I can ignore this term, and I can take this expectation operator right here. Again, these two terms can be ignored. So I can write this as X transpose X inverse multiplied by X transpose expected value of U transpose Now, if you see, this expected value of U transpose is nothing but variance of U. And variance of U, हमने just देखा था, we assume it to be sigma square. And it's a constant, so I can easily take this constant out. So I can write this as sigma square. Now this will become X transpose X inverse multiplied by X transpose X and X transpose X ka inverse. Now this is X transpose X inverse multiplied by X transpose X. This will become identity. So I can easily ignore this. And the only additional term that is left over here is this X transpose X inverse. So I can easily write variance of B as sigma square X transpose X inverse. So, and now you must understand that, this variance of B, since X का क्या dimension है? X का dimension है n by k. Now, when it gets pre-multiplied by X transpose, so X transpose का dimension will be k by k. उसका inverse का dimension will also be k by k. So if you actually notice, this variance of B will have a dimension, or this expression has a dimension k by k. Always remember this. Now, how do I express this? If you actually notice, let us take, for example, that I have the regression equation which is written as simple linear regression function. That is, I have only bivariate linear regression. So इस केस में X transpose X क्या होता है मेरा? X transpose X becomes n summation X summation X summation X square. अब मेरा ये क्या टर्म है? सिग्मा स्क्वायर X ट्रांसपोज X का इनवर्स. सो इनवर्स निकालने के लिए क्या करना पड़ेगा मेरे को? X ट्रांसपोज X इनवर्स निकालने के लिए फर्स्ट आई हैव टू टॉक अबाउट एडजॉइंट ऑफ X ट्रांसपोज X इनवर्स एंड डिवाइडेड बाय डिटर्मिनेंट ऑफ X ट्रांसपोज X इनवर्स. तो डिटर्मिनेंट ऑफ X ट्रांसपोज X इनवर्स आप इजीली निकाल सकते हो. दैट विल बिकम n समेशन X स्क्वायर माइनस ऑफ समेशन X का whole square, right? And adjoint of X transpose X क्या होगा? Adjoint means what? You simply first calculate those minors and cofactors and then just reverse the sign. अभी 2 by 2 है तो इसका adjoint निकालना बहुत ही easy है. You simply reverse it. So I write it as summation X square. Then I have, these diagonal elements can be exchanged with each other and the sign can also be reversed. So summation X, dono same hai, so it does not matter, but I'll have to reverse the sign. And then here I'll have n. So this becomes my adjoint of X transpose X ka inverse divided by the determinant of X transpose X inverse. So it will become n summation X square minus of summation X ka whole square. So this whole term now becomes X transpose X का inverse. अब मेरा variance of B क्या है? Variance of B is sigma square X transpose X का inverse. It means sigma square. Let me write this as whole like this. It can be written as summation X square minus of summation X minus of summation X n divided by n times summation X square minus of summation X का whole square. Now, if you actually see this summation x square minus summation x ka whole square can also be written as n times summation small x square. Just do this. You'll easily find out that this can be written like this. That is, it can be thought of as summation xi minus x bar ka whole square, that is equal to summation x square. Now, what it says is that when you write variance of B in this form, all the elements on the principal diagonal will be your variance of B0, variance of B1, variance of B2, so on, variance of Bk if there are k number of explanatory variables, and all the elements on the off diagonals, they are covariance of B0 with B1, covariance of B0 with B2, covariance of B0 with B3, so on till covariance of B0 with Bk. And that's why it is called as variance covariance matrix of OLS estimators, where the elements on the principal diagonal gives you the variances of the OLS estimators, and all the elements on the off diagonal will give you the covariances term. So here, if you actually calculate this, so this divided by this multiplied by sigma square will give you variance of B0. This divided by this multiplied by sigma square will give you variance of B1. So अगर आप actually इसको expand करो, this will be n divided by n times summation small x square multiplied by sigma square. This gets cancelled out, and hence your variance of B1 in case of bivariate linear regression can be easily written as sigma square upon summation x square. Now, if you actually go back, in your undergrad class, you'll exactly find out that you exactly write your variance of B in this form. But this is a simple, example of bivariate linear regression function. Now, if you just simply remember that variance covariance matrix of B is written as sigma square x transpose x का inverse, और अगर आप deviation form में लिखोगे तो that will become small x transpose x का inverse sigma square. If you just have this term, you do not need to memorize variance and covariance formula of OLS estimators. So now I have mean of B, I have variance of B, so I'll write this as B is distributed with mean beta and variance sigma square x transpose x inverse. Now if you assume the sixth assumption which I had told you in our previous lecture, that it need not be assumed at all, but you assume the normality of error terms, your B, that is OLS estimator, will also become a normally distributed random variable with mean given by beta and variance given by this term. So this is your mean and variance of beta. You need not write anything because all of this are given in the notes. One thing that you notice here is sigma square is a variable or is a parameter which belongs to the population. This is population variance, which we do not know. And since we do not know this population variance, it means we must use an estimator to estimate this population variance. And it is where we use a very important estimator which we call as standard error sorry, of estimate or standard error of the regression, where sigma square gets estimated by a sample estimator which is written as S square, which is equal to RSS divided by n minus k. So since we do not know about this sigma square, I cannot calculate variance and covariance of B. And since this is a population parameter, I must use estimator to estimate this, and the estimator, which is an unbiased estimator of sigma square. What it means is that expected value of S square is equal to sigma square. So the unbiased estimate of this unknown population error variance is estimated by S square, which is equal to RSS upon degree of freedom, that is n minus k. And if you take the under root of this term, that is under root of S square, that term is referred to as S, and it is called as standard error of regression. Regression. And normally when you have output results from the software, you'll find that they give you the standard error of regression as well. So this standard error of regression is an unbiased estimate of the unknown error variance, which depends on the residual sum of squares divided by the degree of freedom in the model. I give you a task which you must do while practicing at home. You must find out variance covariance matrix of a population regression function, which is this. So again, a homework, you have to find out variance covariance matrix of the OLS estimators for the population regression function expressed as this. That is, you have to find out the variance covariance matrix of multiple linear regression model. In this case, we have only 3 explanatory variables including the constant. So you have to find out the variance covariance matrix of B. Okay, all right. So I'll stop here. There's an important announcement that I had a word with Savita ma'am. She wants your lecture tomorrow. She wants a lecture tomorrow. One second, guys. Good morning, ma'am. हाँ मैम बोलिए ना. बस मैं आज ही भेजूंगा, लेक्चर में हूँ मैं. I'll send it. अच्छा ठीक है, मैं भेजता हूँ. मैथ और मैक्रो दोनों ना? नहीं वो दोनों पेंडिंग है ना मैम, मैं भेज रहा हूँ अभी. हो गया मैम, ऑलमोस्ट हो गया. मैं लेक्चर में हूँ, 1 घंटे के अंदर I'll send. हाँ ओके. Sorry. I had a word with Savita ma'am. She wants to lecture tomorrow. Tomorrow's lecture at 9:30 will be conducted by Savita ma'am. I think that will be class of development. So I'll stop here and just revise whatever we have done till today and do these 2 homeworks. Also, since we have a 1 week time, I request you to do the computer exercises of the chapter multiple linear regression. I guess it's chapter 3 from the book Woolrich. Do at least 5 computer exercises, and if you wish you can submit them to me. Either you can do it on R or Excel, they are easily doable. So at least 5 computer exercises from chapter number 3 of Woolrich. Please take it as a homework, and you can just submit in this week's time because we have a 7-day gap. So I request you to solve these computer exercises. At least 5 you can send me, and if you're interested you can solve more as well. So I'll stop here. If there is any question, please ask.
Sir, Will ma'am be continuing from here, or will she be teaching something different?
No, she wants, she has a lecture of development eco, I guess, with MSc Eco people.
So that means FE will not have a lecture, right?
Yeah, FE will not have a lecture. MSc Eco and agribusiness guys will have development eco lecture.
So what can we expect for the periodical, and when would it be?
Periodical का date तो मुझे नहीं पता है, but periodical में you expect MCQ and it will be an open book test.
So whatever we would be covering till like what date can we expect that? Because like, according to the timetable that we received
Till
earlier,
today.
so till today, right? After
Yeah.
today, like, okay, sir. All
No.
right. Thank you.
So till mean and variance of B, and your MCQ will consist of negative marks as well. And it will be an open book test. So, yeah.
So could you just repeat that part?
Negative marking.
Oh, there would be negative marking. All right.
Haan ji.
Okay, sir.
So there will be 5 questions of 2 marks and 10 questions of 1 mark. 1 mark will carry a negative marking of 0.25 and 2 marks will carry a negative marking of 0.5. Is that clear?
Yes, sir.
Okay, all right.
Sir,
हाँ जी.
sir, could you just explain once again that from variance of B, like the previous step, how did you come to sigma square by sigma of x square?
कहाँ पे dear?
So just scroll up. Here. Yes, sir. From
Ye?
this step. Yes, sir.
ये portion?
Yes, sir.
Yeah, I see. This is the formula of variance, dear.
Yes, I get that.
हाँ, तो ये जो है n times summation big X square minus of summation X का whole square, it will also be equal to summation of X minus X bar का whole square. That's why you can easily write it as n times summation X square. You expand this, you'll find out that this and this are equal.
Okay, got it, sir. Thank you.
Variance of X आप ऐसे भी लिखते हैं ना, अब मुझे expectation of X square minus of expected value of X का whole square, right? That is nothing but I've written this only, nothing else.
Yes, got it.
Sir, just another question. So when you are
हाँ
saying
जी.
like there would be a 10 marker, so are we expected to do something on Excel or R? Like would it be an
It
exercise?
will be a copy, pen copy test. Yeah.
No, I mean like we would
No.
not be, we would not have to solve any regression something on Excel or something. Would or like the
Excel
example
पे नहीं
that
हुआ
we-
कर. हाँ जी,
No, the
Excel पे
kind
करना
of-
नहीं होगा.
Okay.
But you have to solve 10 questions manually.
Okay, because
Sir,
the
10
last
marker for
exercise.
tutorial.
क्या बोल रहे सेतु?
Sir, he's asking about 10 marker. Is it for tutorial?
Yeah, it's for periodical 1. That you are supposed to have
10
on
markers.
26, right?
Okay, sir, one more question. Looking at the calendar, like Rahul said, ideally they should just be from next week itself, from Monday. So since we don't have a class tomorrow, should we just assume that whatever you've covered up till now, approximately 5 to 6 lectures, that will be the syllabus for the youth?
I mean, you just mentioned this, Ali. I think till today, whatever we have covered is your syllabus.
Okay, so sorry.
Just mention.
So my intention to ask that question was because like we did an exercise in the class using Excel wherein like we had to solve for betas, right? So
Yeah.
I'm just asking you if we can expect something of similar sort,
No,
or would
no,
it be like no, okay,
Yeah,
sir, all
No.
right.
So you can expect questions of the sort that are asked in IJDR or ISI or Delhi School. Such type of questions I'll ask as MCQ, which are based on whatever we have covered.
All right,
Nothing
sir.
out of syllabus. Okay.
Yes, sir. Thank you.
Okay. Okay then. All the best, and just guys stay safe. Even I have come back home because the situation in Pune is really worrisome. Also, situation in my state is also not that good, but I'm home, I'm safe, and I hope you guys also safe. Stay safe, take care of all others around you, and see you in the next class. Thank you so much for being in the class today, and see you next.
Thank you, sir.